Alright guys, follow me. Whoa, RGB!
Are you ready to spark your imagination? Hold on to your keyboards and prepare to have your mind illuminated as we turn the spotlight onto the future of LED technology. Greetings, light hackers. Welcome back to Dave's Garage. Today is not just any other episode, it's a game changer that's been 5 years in the making. We're going to unveil an amazing new LED hardware board and an open source software project that promised to revolutionize the way we use LEDs. This could be the key to creating the most compelling, mesmerizing, and practical LED effects you've ever seen. Coming up, I'll tell you how you can get me to send you one for free. So buckle up, folks, grab your gear, summon your inner tinkerer, and let's dive into this photon-filled adventure together. Join me today in Dave's Garage, where darkness fears to tread. Hey, I'm Dave. Welcome to my shop. I'm Dave Plummer, a retired operating systems engineer from Microsoft going back to the MS-DOS and Windows 95 days. And today in Dave's Garage, we're going to explore the Night Driver LED system as we focus on one of its most compelling projects, the Mesermerizer. This is a project I've been working on since 2018, learning as I went. I'm going to take you on that journey as I look back at my LED adventures and then show you the culmination of those efforts, the Mesermerizer itself. We'll even walk through the creation of the custom PCB using JLC PCB's Easy EDA editor so you can see how to order turnkey surface mount PCBs that arrive at your door, fully assembled and ready to run. Now, this all began about 5 years ago when I decided that after spending an entire career writing software, it was time to improve my hardware skills. Naturally, I was most interested in digital electronics, so I grabbed myself some breadboards and an Arduino Uno. I started where most of you do as well when you first pick up an Arduino, with a single LED, and then I made it blink. It's trivial, of course, but seeing a real-world manifestation of my code running was something of a rush. It was kind of like the first time one of my programs made the computer do something useful, the same kind of dopamine reward. Next, I wanted to control the color of the LED and extend it to many LEDs, so I grabbed an LED strip off of Amazon and set about learning how MOSFETs worked so that I could control the red, green, and blue channels of the strip, and pretty soon, I had a board with a dial that allowed me to change the color of the entire strip at will. Setting the whole strip to one color is all well and good, but it doesn't allow you to do anything interesting in terms of effects, so I investigated and soon ordered an individually addressable LED strip. That's where you control the color and brightness of every LED on the strip independently. There are a few different types, but the most common is a WS2812B style, and that's what we'll be using today. They're also sold under the NeoPixel brand name. About that time, I moved to the ESP32 chip as well, which has Wi-Fi and Bluetooth built in, as well as 2 powerful processing cores and 520K of RAM. It still supports the Arduino IDE, and almost everything you know about Arduino programming still applies. It's just a much more capable chip than most of the AVR lineup. An individually addressable LED only has 3 wires: power, ground, and data. The data line carries a square wave signal that contains the color data for the LEDs. It's simply 3 bytes per LED, one each for red, green, and blue. It's up to whatever chip you're using to create and send that signal to the strip. Keeping that information in the dark where it belongs is up to the Fast LED library. After linking your project with Fast LED, you can just hand it an array of color objects and it immediately sends them out to the LEDs without you needing to know anything about how it's done under the covers. It just works. I used it to build a project that put an LED strip up on the ceiling edge of my workbench in the shop. And in fact, that was my very first YouTube video of all time. I set it to the flame effect and the video title was, "Help, my shop's on fire with LEDs." The project is still running today and it has a wall-mounted control box with a rotary dial that lets you enable and disable effects and select the active one and so on. Now, a smarter man would have used a touchscreen, but the rotary dial works well enough. The next big project that I wanted to tackle was my patio umbrella. The fact that it had 8 spokes and I had an ESP32 that had 8 parallel LED channels meant it was predestined, I figure. I updated the code to draw to multiple channels at once while also allowing me to write different effects to each spoke. Each spoke gets connected to a different ESP32 pin and the fast LED code draws them in hardware in parallel using the RMT signal support of the chip. Pretty soon I had flames and fancy effects running on all the spokes and it's become one of the most talked about features of my backyard. Everybody seems to want one, but nobody wants to build one on their own. If you can manage the wiring, the code's all on GitHub. Drawing to multiple channels wasn't going to be limited to the great outdoors, however. I bought an LED chandelier off eBay, turned it upside down, added a stand and a base, and then stripped out the factory white LEDs in favor of a short individually addressable strip in each of the 4 arms. Each arm is connected to a different pin on the ESP32. The atomic fire lamp was born, naturally with flame effects, but also with a host of other interesting visualizations as well, many of which are also music reactive. But what could be more fun than an LED strip? Why, an array of them, of course. And so that was my next step. I ordered 2 16x16 LED panels, and as soon as they arrived, sat down to write code to scroll a message across them as a first test. I'm going to teach you a new word today, the boustrophodon. That's because in pursuit of simpler wiring, most 2D matrices that are made up of individually addressable LEDs are woven back and forth, so that as you go down the matrix, each second row is backwards. This creates a pattern that resembles the efficient manner in which you might plow a field, and hence the name derives from the phrase, as the ox plows. And now you know what a boustrophodon is. I decided at that point that I wanted to make a spectrum analyzer. One of those fancy bar graphs that displays and breaks down the music into bands and shows you the relative sound level in each band. I'd seen a friend make one out of discrete electronics back in the 80s, but I figured today I might be able to do it in software, so I got a microphone module, hooked it up to one of the input pins on the ESP32, and started hacking away. Now, I didn't know anything about the ESP32's I to S capability at the time, so I just did the naive thing. I sampled the value of the ADC pin in a tight loop and used that to build a sample buffer. Then I ran an FFT on the buffer to break it into frequency buckets, and I used those buckets to calculate how tall each of the bars should be. Some quick rectangle drawing code, and I had a working spectrum analyzer. The only problem was that my naive sampling kept the CPU busy half the time. But thanks to the hardware support of the ESP32, you can use the I2S protocol to DMA the sample results right from the DAC into memory, allowing the CPU to continue on its merry way doing other productive work. That freed up enough CPU cycles that I could spend my time writing some more graphics effects. Adding music reactivity to the other effects was fairly simple. I just kept a weighted average of the VU, or volume units, that I was already sampling in the spectrum analyzer code. But even better would be beat detection, where the chip listened to the content of the music and then decided which loud transients were actual true music beats. The whole process is beyond the scope of this video, but the basics are that it watches for transitions from low to high volume and then isolates the ones that occur a significant distance apart with some regularity. I used a set of clear glass power line insulators that my grandfather had collected and passed down to make a light reactive organ. I put an LED ring in each one and added code to make Night Driver aware of drawing to circular canvases, and it all worked really nicely. And you know what else is round and has LEDs? PC fans. When I made that realization, I bought a Leon Lee PC XL case and equipped it with 10 fans that each had individually addressable LEDs. I decided to wire their data lines so as to cascade from one to the next, making them simply a long sequence of LEDs rather than 10 short segments. I then added code that could draw to any clock position on any individual fan and was able to create a number of cool fan effects for my PC case. One of my favorites is the tape reel effect, which recalls the old IBM tape drives of the 1960s and 70s. By virtue of picking up the sound code that was already in the project, many of the PC fan effects are also sound and beat reactive. The next big feature I wanted to add was remote drawing over Wi-Fi. I wanted to be able to write my effects on the PC, a Mac, or Linux box, and then send the results directly to the matrix over Wi-Fi, whether it was a strip or a matrix. To that end, the first thing I did was to set the clock of all the client devices from a local or remote NTP server, which would normally get the clock synced within a few milliseconds. Now that every device had a consistent view of the time, the PC could break the work up into multiple segments, each to be sent out to its own ESP32 over Wi-Fi. It would compress the color data, stream it to the ESP32s over a Unix-style socket, and run a dashboard to display what was going on. The ESP32 buffers a few seconds at least worth of color data, so any blips in the Wi-Fi shorter than that are smoothed out, and because each chip has the same clock and the frames are perfectly time-stamped, they all play in unison. This synchronization allows me to have effects where the drawing spans multiple different, completely wireless ESP32s. The code to send the color data to the ESP32 can be written in pretty much any language that supports arrays. I've done it now in C, C#, and Python. I even made a Unity project that visualized the LEDs on the PC side as it sends the packets out. If you'd be interested in writing some test code to drive the matrix in Python, please stay tuned for information on how you can get started. Here's a quick example of the hidden Christmas lights that I added to my cabana. The effects range from twinkling lights to ambient light strip to fireworks. This is the fireworks effect, generated and running in C# and running across at least 5 different strips of up to 8 meters each. The control software runs in a VM on a machine in my shop, and it in turn controls about 15 different installations around the property. In any event, about that time, I stumbled across the technology used in jumbotrons and Las Vegas billboards, the Hub 75 Matrix. The Matrix has a 16-pin input connector on the back, and rather than having a single data line, it basically operates like a big shift register. You give it a chunk of DMA memory, and when combined with the Smart Matrix 4 library, it will dutifully draw whatever is in your buffer. The hardware support in the ESP32 means that it can all be drawn via DMA, which keeps the processor free from the heavy lifting of drawing the display on its own. In addition to power and ground, connecting the matrix requires about 12 GPIO lines, and so it's quite a mess if you have to hand-wire your matrix to the ESP32, which is what I'd been doing up to this point. But soon enough, I found a small hardware board from AZSMZ on Tindy that contained an ESP32 chip, a power connector for the matrix, and a connector that allows it to plug into the matrix's back connector with no manual wiring. I had to add my microphone to the circuit somehow, so I hacked the board and wired that in on a spare pin, and then I added a second input to receive commands from an infrared remote control. The remote would allow you to change colors, switch effects, and so on. I cobbled all of that together and it worked, but I still had a wish list of features that were missing. For one, I wanted the microphone and IR pickup built in, not hanging off by wires. Second, I wanted to make it use USB-C. Third, I wanted to use what's known as a dual UART so that when you plugged it in, you'd actually see 2 serial ports, not just one. Even though you connected to them over the same cable, you could then use one port for debugging and the other for programming and serial logging. That gives you the ability to do single-step source debugging in Visual Studio Code. And finally, I wanted some additional PS RAM on the board for a total of at least 4 megabytes. The problem is that nobody made a board with all those features, and certainly not with a Hub 75 connector built right in. And that's when I got the big idea that I'd make it on my own. But before I tell you that story, let's have a look at what the Mesermerizer is capable of. First, we'll do the hardware installation. All we need to do is to plug the PCB directly into the matrix and connect the power lead. The only wiring that you have left is to plug it into a USB port. We would normally customize things like your zip code for the weather and join it to your Wi-Fi, but even without those steps, the Mesermerizer starts working as soon as you plug it in. Here's a quick tour of just a few of the capabilities. The board continually samples digital audio using the built-in mic, or you can plug in a 1/8" audio jack in directly, which will automatically disable the mic in hardware. The first effect that comes up is the classic spectrum analyzer. There are about a half a dozen variants of it with varying numbers of bars and color schemes, and I was truly impressed by the ESP32's ability to not only sample and process the audio at 50 frames per second, but to draw the spectrum at up to 100 frames per second. There are only 2 cores at 240 MHz, but that's really quite fast for a microcontroller, and it really shows in the snappy performance. The next effect is a clock, but with a twist. It's a pawn clock where 2 AI players battle, and the score display is the current time of day. It's not rocket science perhaps, but I'm still proud of the code I wrote to predict the ball path while taking into account any number of bounces. The players play quite well, but the ball accelerates periodically, ensuring that eventually someone will miss, and the time will be updated. Next comes a YouTube subscriber counter set by default to my own channel. I'm probably sitting at home right now staring at this display as you're watching this, so do me a solid and make sure you're subscribed to the channel. You can imagine me watching the number change as you click the button. With this effect, I'll be the first to know about it. Next, we have your local weather, which is based on your zip code that can be optionally set through the web interface. It displays the current temperature, the day's forecast, and the forecast for tomorrow as well. Right now, it has some childlike drawings of weather patterns, but if you have the artistic skill to draw great weather icons at a mere 16 by 16 resolution, please get in touch and you can contribute your art to the project at nightdriverled.com. Next comes the ghost wave effect and a couple of other waveform effects that visualize the current audio waveform in different ways. I'm pretty happy with how these turned out, and they can be really entertaining to watch, kind of like seeing Laser Floyd at the Pacific Science Center. After that, we have Conway's Game of Life. In case you're not familiar with it, it's a simulation of organisms that are born, grow, and die depending on how many neighbors each one has. The board is randomly seeded to start, and then the game plays out by the set rules. If you watch long enough, you might see the evolution of creatures ranging from simple walkers up to projectile-hurling cannons. Because the board supports buffering of Wi-Fi frames, I can even stream video to it. Here's a quick Python app that I wrote in order to push video from YouTube out to the matrix, and if you watch closely, you'll see that you've just been rickrolled. As long as the module you're using has some PS RAM, the system buffers up to about 10 seconds of full-screen video, so the playback is perfectly smooth even on imperfect Wi-Fi. While there are a solid 30 different effects built in, there's just not time to cover them all today, so here's the last one we'll look at for now, the circuit effect. It simulates electrons flowing on a PCB that is built on the fly as the particles travel around. And speaking of PCBs, as I mentioned earlier, I really wanted to create my own ESP32 system that plugged directly into the matrix and included all of the features from my wish list. The big complication was that the board would be all tiny surface mount stuff. It would have something like 37 components on it, and I had no interest in hand soldering them all if I was going to provide them in any quantity. I looked around the marketplace, and after trying a number of options, I finally settled on JLC PCB. Now, while I could wax on at some length about their great production services and stellar customer service, the main reason I picked them was because they offer a great online piece of circuit design software known as EasyEDA. Not only was it my favorite editor at this point, it's also free, but it had one killer feature that I couldn't find elsewhere. You can actually order the board you're working on, completely assembled in turnkey with all its components, ready to go from within the editor. You don't even have to know what a Gerber file is or how to make a bill of materials or anything. The software does it all for you, and JLC PCB does all the production and assembly in-house. For someone like me who's afraid of trying to make a surface mount PCB, it's a perfect fit. Let's go on a little tour of EasyEDA so that I can show you how you can go about it. Once I load up the EasyEDA website and log on in, I'm taken to my projects. I'll open one of the schematic projects I've worked on in the past, and we'll zoom into a random resistor. Laying out a schematic is the same basic procedure as any other EDA you might have seen in the past. You place components, you rotate them, and then link them with wire connections. The one thing that makes the EasyEDA process so compelling, that ability to single-click order a finished product, is predicated on you taking the time to select the actual physical part that your schematic symbol represents. That way, when it comes time to actually make the board, the bill of materials and the pick-and-place files and the drill files are all generated automatically for you, and you don't have to worry about them. Choosing a part also usually includes the component's footprint, and so your PCB design is also predicated on the selections you make here. We can see with this resistor that when we select it, the component properties come up in the right-hand column. In this case, the footprint of the resistor, which defines its place on the PCB and what it should look like, is an R0805. That means it's a resistor that is 80 mils by 50 mils. For our metric viewers, that's a 2012 as in 2.0 millimeters by 1.2 millimeters. We can also see that the supplier part number has been set. This takes just a few seconds to do, and it's what enables your project's automated production. EasyEDA is tightly integrated with the LCSC catalog, including real-time inventory, and so it makes finding your part quite painless. You can also specify parts from Mouser, DigiKey, and a few other major players. In this case, it's a part from LCSC with part number C17414. When your schematic is ready and you're about to move on to the EasyEDA PCB editor, you should run the design rules checker before doing so. It's very thorough and will prevent you from building a PCB from a broken schematic. Once the design rule checker passes, you can launch the PCB editor. When you do so, all of your component footprints will be shown along with blue lines that connect the pads that you will need to route. There's also a reasonably capable auto router, and if you need more power than the auto router can provide, you can download a copy of the auto routing engine and run it locally on your PC. Either way, once your component arrangement and routing are done, and your silkscreen layer says whatever you want it to say, it's time to order your boards. From the fabrication menu, we click One-Click Order PCB. This is where the magic happens. The EasyEDA software will create the Gerber files, bill of materials, pick-and-place files, drill files, and everything else needed to produce a PCB and assemble it based on the information you provided at design time. It will then automatically upload that info to the JLC PCB system so that you can review pricing and options. Once it's uploaded, we can click on the Gerber Viewer link to see what our produced board will actually look like. There's even a 3D viewer, and it incorporates models of the most common parts as well, so you get a fairly good rendition of the board that you can spin around in place and inspect to your heart's content. Back to the PCB order page, I'll accept defaults for most everything, but let's set the PCB to be purple just for something different. I do have to select the standard PCB instead of the economy PCB assembly style because my board requires assembly on both sides. I could likely save a lot of money by hand soldering the single backside connector, but I'm trying to keep it turnkey and easy, so today I'll pay for the privilege of having it delivered complete. When I click Next, I'm taken to a preview of the PCB, and from there I can click Next again to proceed to the bill of materials. I click Process, and it will show you the list of components that your board needs and where they go. If any of the parts you've ordered are out of stock, you're given the option of browsing their catalogs for an alternative or leaving the parts out if you absolutely need to. Next, we get a component layout preview, and finally, after that you'll be given the pricing and delivery window. When you check out of the cart, you initiate a process that includes the PCB production, parts picking, assembly, soldering, packaging, and shipping. All you need to do is wait for the big yellow DHL van to show up about a week later, and there are also a few expedited options if you need it sooner. Here's an example of the board as it comes out of the packaging. It's completely ready to go out of the box with no hand assembly other than connecting your power wire required. You can simply plug it in and enjoy. JLPCB has agreed to sponsor this episode, but rather than paying for the privilege, what I negotiated is that JLCPCB will produce a batch of the hardware boards for me to distribute to viewers who want to contribute to the open source codebase. Priority will be given to contributors on GitHub that have React experience and are willing to tackle the embedded user interface that allows you to configure effects and settings. But even if you just want to work on the C++ side with the ESP32, or write a Python client program for the PC, or create cool new effects, please do get in touch with me at nightdriverled.com. The more folks that we have working on the JLC PCB board, the better. Remember, you'll also need to source a Hub 75 matrix, and it should be a 64x32 and ideally 3mm pitch. You can find them on Amazon and eBay and AliExpress, and I'll put a link to a few in the video description as well. If there's sufficient interest in this episode, I'll look at doing a code introduction walkthrough for the Night Driver LED codebase next. In the meantime and in between time, hope to see you next time, right here in Dave's Garage.